Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying matrices and determinants lecture 1. So we'll be talking about basic definitions of matrices in this lecture. So let's start with the definition of matrices. So matrices are a rectangular array of numbers. For example, A1, A2, A3, A4, A5, A6. Or we can also write a matrix as A1, A2, A3, A4, A5, A6, or we can also write in this format A1, A2, A3, A4, A5, A6, A7, A8, A9. So basically, there are multiple ways to write different kinds of matrices. The main thing is it's a rectangular array of numbers, right? Now let us talk about the building blocks of a matrix. So let's write a standard matrix. A11, A12, A13, A21, A22, A23, A31, A32, A33. So this is a very standard matrix. Now the horizontal ones are called as rows and the vertical ones are called as columns. So you can, if you are forgetting this by any chance, you can remember this as HR and VC. We all know VC and we all know HR. So HR means horizontal rows, VC means vertical columns, right? So you can remember these abbreviations for remembering the notations of matrices. Okay. Now the first term, what is this A11, A12? So how do we define it? So basically, if we are talking about one Aij over here, then this is the row in which it's present, the element is present. Basically, it's the row, and this is the column. So basically, this tells us, this A11 tells us that this particular element is present in the first row and first column. So this one tells that it's present in the first row, second column. So basically, the first is always row, second is always column. Now, this was about rows, columns, and now let's talk about the order of matrix. So this is how we define Aij M cross N, right? Again, M represents the number of rows, N represents the number of columns, right? So again, rows first, rows column second, rows first, column second, right? You have to write in this format only. So this is how we have to define the order of matrix: number of rows cross number of columns, right? And notations we have already defined: I and J, row and column. Now let us talk about the types of matrices. So the first one is null matrix. So in case of null matrix, every element is zero. So this is defined by O, and that is basically every element is zero. It can be square, it can be rectangle, it can be vertical, it can be anything, but the main thing is every element is zero and it's defined by O, right? Now, if we talk about the horizontal matrix, we can obviously understand with the help of name that horizontal means it's, on the linear side in the horizontal direction. So basically that means number of columns are greater than number of rows. In case of horizontal matrix, number of columns are greater than number of rows. And similarly, in case of vertical matrix, number of rows are greater than number of columns. This is for horizontal matrix, this is for vertical matrix. Now if we talk about the row matrix, so row matrix is a special case of horizontal matrix. In case of row matrix, we have just one single row and multiple columns. So basically, in case of row matrix, we have just one row. So it looks like something of A, B, C, D, something of this sort. This is how a row matrix looks like. And in case of column, we have just one column. So this looks like 1, 2, 3, 4. This is how a column matrix looks like. Now, if we talk about the square matrix, then as the name suggests, it's kind of obvious that rows and columns are equal. So rows and columns are equal. Number of rows and number of columns are actually equal. So let's say this is A, B, C, D, E, F, and G, H, I. So this is how a square matrix looks like. So let me just give a summary of all these things. In case of null matrix, every element is zero. That is the basic condition. In case of horizontal matrix, number of columns are greater than number of rows. In case of vertical matrix, the vice versa condition is there. Number of rows are greater than number of columns. In case of a row matrix, we have just one single row. In case of a column matrix, we have one single column. And in case of square matrix, we have equal number of rows and columns, right? Now let's talk more about the square matrix. In a square matrix, the pair of elements Aij and Aji are called as conjugate elements. So let us write a standard matrix first. So this is A1, A11, A12, A13, A21, A22, and A23, A31, A32, and A33. So this is a very standard matrix, square matrix, right? Now the elements like A12, A21, A13, A31, A2, A23, and A32, these are called as conjugate elements, right? Now, if we talk about the elements A11, A22, A33, basically of the format AII. So these are called as diagonal elements. And the line, this particular diagonal line is called as leading diagonal or principal diagonal. Now you must be thinking that this particular line also can be called as diagonal, but in matrices we define only these elements, diagonal for these elements, basically AII. So we have elements called as AII, and along these elements we call it as leading diagonal or principal diagonal. Now the third point is trace of A is defined as sum of elements along principal diagonal. So basically sigma AII, where I goes from 1 to I equals to n. So where n is the order. In case of square matrix, order is n into n only, right? So that is why you can write n over here. So this summation is called as trace of A. Now interesting thing over here is you cannot define a diagonal, leading diagonal or principal diagonal for any matrix other than square matrix. So whatever we are talking over here, conjugate elements, principal, leading diagonal, trace, all are defined for square matrix only. Don't try to apply these concepts in any other matrix. Now let us try to understand the types of square matrix, and the first one is triangular matrix. So again, triangular matrix is being divided into two parts. The first one is upper, the second one is lower. So upper is defined like this. Let me give an example. So this one is A11, A12, A13, 0, A22, A23, and this is also 0 and A33. So this is how an upper triangular matrix is being defined. So basically what that means, anything below the leading diagonal, principal diagonal or leading diagonal is 0. So any element below the principal diagonal is 0, and this is how upper triangular matrix is being defined. It's not defined based on the upper elements, it's defined based on the lower elements below the leading diagonals. Basically, you can clearly see that Aij, where I is greater than j, in that cases Aij equals to 0, where I is greater than j, Aij equals to 0. This is how mathematically upper triangular matrix is being defined, right? Now, opposite case over here, we have Aij over here and I is less than j, and in that case Aij equals to 0. So you can just write it like this. So that would give me A11 0 0, A21 A22 0, and this would be A31, and this would be A32 and A33. So this is how a lower triangular matrix is being defined, right? Now an interesting point over here is all the remaining elements can be 0. So that is not mandatory that these elements are not 0, but the thing which is mandatory is these lower elements in case of upper triangular matrix and these upper elements in case of lower triangular matrix has to be 0. So this is the basic condition for upper and lower matrices, right? The remaining elements can be anything, 0, non-zero, whatever. Now let us talk about the second type of square matrix, that is diagonal matrix. So over here A11, A22, A33. So 0, 0, and 0, and 0, 0, 0. Now in case of diagonal matrix, we have two conditions. The first condition is anything above or below the leading diagonal has to be 0. So basically what that means mathematically is I is greater than j or I is less than j. In that case, Aij equals to be 0. And the second condition is unlike the upper triangular or lower triangular where we didn't have any kind of restrictions on the remaining elements. Here we have one restriction that at least one of these leading diagonal elements has to be non-zero. So basically, at least AII is one AII has to be non-zero. I'll write it properly. At least one AII has to be non-zero. The remaining two can be zero, but at least one AII. So basically one element of leading diagonal has to be non-zero. In case of upper or lower triangular matrix, the remaining elements could have been anything. It can be zero, positive, negative, anything. But over here, in this case, at least one element has to be non-zero and the remaining elements has to be zero. Okay. Now a special case of diagonal matrix is unity or identity matrix. Right, so that is 1 0 0 0 1 0 0 0 1. So this is the unity or identity matrix. So this is a very special case of diagonal matrix. Now let's look at this example. Minimum number of zeros in an upper or lower triangular matrix of order n. So let's start with an order of 3 and then we'll extrapolate till for the order of n, right? So the basic upper triangular matrix, we are defining upper because or is given over here, so we can either write upper or lower. So this would become A11, A12, A13, 0, A2, A22, A23, 0, 0, A33. So this is how we define a 3 cross 3 square matrix, which is upper triangular matrix, right? Now we can see that the minimum number of zeros will be 3 over here. So basically in the first row will not be having any zero. In the second row we'll be having 1 0. In the third row we'll be having 2 zeros. So similarly, if I try to write down an n cross n upper triangular matrix, what I'll be getting A11, A12 till A1n. So this is the first row. In second row we'll be having 1 0, right? In third row we'll be having 2 zeros. In fourth row we'll be having 3 zeros. So in nth row we'll be having n minus 1 zeros, basically n minus 1 zeros. So basically we are going from 1 plus 2 plus 3 plus 4 plus till n minus 1. So this is nothing but summation of AP. So you can find out the summation of AP for the same. So that would, we'll use the formula of n plus 1 by 2. So over here n is actually n minus 1. So that would be n minus 1 multiplied by n divided by 2. So this is our answer. Now let's look at some properties of addition and subtraction in case of matrices. So a plus b equals to b plus a. So basically in all these cases, the order has to be same. So before studying any property of summation of matrices or subtraction of matrices, we should understand that we can add or subtract only when the order is same. So if order is different, we cannot do anything. So let's say if I'm adding a matrix of 2 cross 3 with the matrix of 3 cross 2, we cannot do it. So we can add 2 cross 3 matrix only with 2 cross 3 matrix. So how does it happen? Let's say the first matrix is A11, A12, A21, and A22. And I'm adding it with, let's say, capital A, capital A11, capital A12, capital A21, and capital A22. Now the final matrix would be A11 plus A11. So basically individual elements will be added for all the elements. For all the rows and columns, individual elements will be added. So this would become A12 plus A12, A21 plus A21, and A22 plus A22. So this is how the final matrix would look after the addition. I can do it the reverse manner. So let's say this is A and this is B. So I can either do A plus B or I can do B plus A. That would fetch me the same answer because A plus B equals to B plus A, and matrices have this commutative property. Similarly, you can also prove that A plus B plus C equals to A plus B plus C, basically associative. I don't need to write every example because that's quite intuitive. And similarly, you can also prove the trace of A plus B equals to trace A plus trace B, because over here I can see that trace is A11 plus A22. Over here is trace is A11 plus A22, capital A11 plus capital A22. And over here is trace is summation of these two only. So if I add both of them separately, I'll be getting this only, right? So that can also be proven very easily. And similarly, the last one can also be proven very easily. So trace property is only meant for square matrix. The remaining properties are meant for the matrices which have same order, right? Now the second property is about multiplication with a scalar number. Scalar is basically any constant number. So in case of if you have studied physics in class 11th, you know that scalar and vector, and basically scalar is a constant number, right? So let's say we have a matrix, and that is A, B, C, D, E, F, G, H, I. So this is a square matrix. And if I want to multiply, let's say 2 over here, so 2a would become 2a, 2b, 2c, 2d, 2e, 2f, 2g, 2h, and 2i. So basically what that means is if I'm multiplying a scalar with a matrix, then every element has to be multiplied with. How? We can write a again as a, b, g, b, e, h, c, f, and I. Now, if I add both of them, then I'll be getting 2a only, right? So that would become with the property of addition, that would become 2 times of a, and that would become 2 times of b, 2 times of c, right? Similarly. So that's how we can prove it, right? So if I'm multiplying a scalar number in any matrix, that number gets multiplied with every element of the matrix. So now I'm stopping this lecture at this point because there are too many definitions to understand in a single lecture. And in the next lecture, we'll be starting with the multiplication of matrices and other properties. So let's meet tomorrow. Thanks for watching.